will be informed. So, this is it. We are live. Muito bem, boa tarde a todos. Bem-vindos a mais uma sexta-feira e a palestra do colóquio do Departamento de Matemática. Hoje nós temos aqui o professor Jonathan Eckstein e o professor Maicon do departamento, que foi o responsável pelo convite. Ele me ajudou a contactar o professor Eckstein e, por conta disso, hoje os trabalhos de condução do colóquio estão por conta do professor Maicon. Maicon, muito obrigado. O palco é seu.
Okay, hello everyone, and thank you very much, Antonio, for the opportunity to bring people here. It is my great pleasure, it's really my great pleasure to introduce Professor Jonathan Eckstein from the Rutgers University, from the Department of Management Science and Information Systems. Professor Eckstein is one of the leading scholars in the area of numerical optimization. He has many important contributions in both discrete and continuous optimization, also in stochastic optimization, which is the topic of today's lecture. He has very highly cited papers. And some of them, for instance, his recent monography on the Admm and operator splitting for statistical learning has more than 14,000 citations, which is quite impressive. And he has also been recognized as an outstanding teacher by the Rutgers community of students. So it's really a great pleasure. I thank you. I thank you very much for accepting our invitation. And today he's going to talk about progressive hedging and asynchronous progressive hedging, projective hedging for convex stochastic programming. So the floor or the screen is yours. Thank you.
Okay, thank you. Okay, so now I do this. Share screen. Screen one. Okay, and okay, so you can see now? Everyone can see the slides now?
I think so.
It's fine.
Okay, looks good. Okay, so so I'm going to talk about some stuff with stochastic programming today. The kind of original algorithm here is something I developed with Patrick Combetz, who was at when I met him, we were both visiting Columbia University in New York City, and he was officially at Paris 6, I think, and actually now he's in the U.S. in North Carolina. Some of the computational stuff I'll talk about at the end, which unfortunately is not really finished or not even close to being finished, but I'll talk at the end a little about how we're trying to put this into practice, and that's some work with J.P. Watson, who's at one of the national labs now on the west coast of the United States, and David Woodruff, who's a professor at UC California Davis, which is near Sacramento, U.S., near the capital of California. Okay, so I'm kind of trying to center this particular talk around stochastic programming, and there's this algorithm called progressive hedging, which was developed right about when I was doing my dissertation research. There's actually slightly before that, actually, there was a working paper in late 1987, and it was published in Mathematics of Operations Research in 1991. So we weren't any faster at publishing things back then, 30 years ago. But anyway, it's by Rockefeller and Wetz, and they knew this algorithm was a form of Douglas-Ratchford splitting in the Admm, but they didn't. They said, we know this, but we're just going to prove its convergence directly. And I can kind of see why they did that, because basically at that time no one knew what the Admm was. Like the operations research community, which is the area of applied math where people tend to worry about stochastic programming, it was really an unknown algorithm, absolutely. I'm going to present progressive hedging from an Admm point of view rather than from the original point of view, which is not really any major scientific contribution. But then I'm going to switch this projective splitting, so that recently I've been trying to attack this same class of problems with a new class of splitting algorithms that's a little more flexible. Okay, so let's get the background for stochastic programming. So we imagine we have some standard kind of scenario tree. So we have T stages here. Okay, I've shown it T equals 3, but it could be a lot more, or it could be 2, or it could be even more. And we say we have N scenarios at the last stage. Okay. And each of those scenarios indexed by I has probably pi I. Okay. And in reality, this is probably some discrete, some version of some more realistic model where we've discretized time and then done some kind of sample approximation of the evolution of the system. Then the real system might be in continuous time and might have continuous random properties, but we've kind of downsampled that to discrete time and some like finite representative tree of scenarios. And so the idea here is that we're trying to optimize some system, and the system will start at the root here and walk randomly down to one of the leaves with some specified probability. So maybe it'll first go here, and maybe then it'll go there, for example. Okay. And at each step at the beginning, and then at each subsequent step, we decide some stuff. Okay, like how much of an investment to buy or sell, or how much to run a power generator. And there be constraints on that, and the constraints may also involve the decisions you made earlier in time. So I know in Brazil, there's models like this get used for hydropower planning. But the general rule is, okay, the model alternates decisions with uncertainty resolution. Okay, so like we make a decision, then we find out which of these 3 nodes we go to, we make another decision, then we find out which of these nodes we go to, and then we make a final recourse decision, and the game is over. Okay. And generally one is trying to, say maximize or minimize minimize expected cost or maximize expected profit over this process. Okay, so the sort of key idea that Rockefeller and Wetz had was to replicate decision variables. So we kind of natively think of there being decision variables at each node of this tree. But what they do is they just spread out the tree so that there are n copies of the decision variables at every stage. Okay, so we kind of unfold this tree into a grid. Okay. And we'll say, so this is kind of like, okay, this is the situation if right at the beginning you could see the future and see exactly which path you would take. Okay. And so now we have like here, there's say 6, n equals 6 different end stage, final stage scenarios. It's like now I just know which of those 6 paths to those 6 scenarios I'm going to take in advance. Okay. And I'll say XIS is the vector of decision variables for scenario I. So let's say it's a scenario I at stage S. So say here, this is like, I equals 3 and S equals 2. Okay. And then X sub I, and then this cursive X sub I is a set of all variables pertaining to scenario I from all the stages, and we'll call like a member of that like little xi. Okay, so all these things. So it's kind of like here, like if I knew in advance that I would end up at this node, these are all the decisions that I would make. Okay, and then I'll call the whole thing. Okay, I'll call the space of all these decisions like cursive X. Okay. All right. And now there's another, we call this space Z is going to be all the same. So the space cursive Z sub I is capital XI without the last stage. Okay, so it's just everything except the last stage. We kind of forget that the last stage, those final recourse decisions are there. Okay. And then this cursive Z is a product of all these. It's all the decisions except the ones at the last stage. Okay. And now this is a word that Rockefeller and Wetz donated to English, which is extremely hard to say. Okay. But it's called non-anticipativity. Okay. But the idea is this is a subspace of this Z. So we forget about the last stage. It's a subspace of this Z that says, okay, you actually can't see the future. So the decision you have to make in these 6 decisions here that are associated with these 6, these n decisions here that are associated with the last stage scenarios actually all have to be the same. Okay, but that's just a linear subspace constraint. All these vectors have to be the same. And then at intermediate stages, all the decisions that are, say, associated with this node actually have to, this node is associated with 2 paths with 2 end stage scenarios. Those 2 have to be the same. Like these 2, these have to be so forth. Okay. So if we impose the constraint that we're in this subspace N that meets these constraints, then all of a sudden now we're back to having a reasonable solution to the actually having a solution to the stochastic program that doesn't see the future. Okay, that isn't anticipative of the future. Okay, and so now Rockefeller and Wetz used a probability weighted metric. Okay, on Z. So they instead of using the normal inner product on canonical inner product on this Z, they just weighted each scenario by the probability of that scenario. So they use this inner product. And when you use that inner product, then projection onto this subspace, projection onto this subspace is kind of what you'd think. If I have a set of variables and, decisions that are all different here, I would just average them, okay? But you actually average them weighted by probabilities. And then at subsequent, at other stages, you average groups of these vectors that correspond to the same node in the decision tree, but you always group them weighted. You always average them weighted by their probabilities, which is what this somewhat, complicated formula is trying to say. Okay. All right. So what I'm going to do is I'm going to apply. We'll assume we have a convex problem here, and we're going to apply the ADMM. So, okay, so far I've just shown you a formulation of Rockefeller and Wetz from like 30 years ago with some minor notation adjustments. But now I'm going to derive that same algorithm using ADMM as opposed to by first principles, which is what they did. Okay, so here's the notation I'm going to use for ADMM. Okay, this f is some function from this abstract space X to the reals, but also plus infinity, and we'll say it's convex. And G is from Z, from some abstract, G is from this abstract case Z to the reals and infinity. And then we suppose we have some linear map from X to Z called M. Okay, and we look at this problem here. So it's minimize f of X plus G of MX. Or equivalently, minimize f of X plus G of Z subject to MX equals Z. And the ADMM for this standard formulation is this thing. You take the augmented Lagrangian of this problem, you minimize it with respect to X, you minimize it with respect to, and then you hold Z fixed and you minimize it with respect to X. Then you hold X fixed and you minimize it with respect to Z. And then even though this may not even come remotely close to minimizing the augmented Lagrangian of this problem, you just update your Lagrange multipliers, which here I'm calling W. Okay, just do the standard update. Okay. All right, so what I need to do is I need to get the stochastic program into this form. Okay, and so this is how you do it. Okay, so okay, so this Fi, okay, is going to be given by, okay, so this is on this abstract space X, okay, where we pretend we can see the future, and you have a separate, say, first or second or whatever stage solution that you can apply to each end node of the tree. Okay, and we say, okay, the cost function I'm going to use there is Fi. Okay, I'm going to call these Fi's. Each one goes from Xi, so this is for scenario I. I'm just going to set it to the cost of scenario I and plus infinity if any constraint in scenario I is violated. Okay, and then I scale it by this pi I that's a probability of scenario I. Okay, and then mi is the map from xi to zi. Okay, that just drops the last stage variables. Okay, so that's a linear map. Okay, so H basically encapsulates all the costs and constraints across all stages in this hypothetical situation that I know at the beginning that I'm going to end up in scenario I. And then, so the stochastic program then becomes equivalent to this thing. It's like, okay, minimize the sum of these Fs such that, you know, M1, X1, M2, X2, et cetera, Mn, Xn, you take those all together, they're in the non-anticipative subspace. So this is saying that, okay, now I'm going to impose, I'm going to have here like I just take the costs weighted by probability, kind of like I could see the future, and then, but I say, oh no, but I have this constraint that I can't see the future. Okay. And we don't have to worry about that. It's the reason we're dropping that last stage is because we don't, you know, once we know we're in the last scenario, it's not important whether we can, there's no need to link to any other scenario to worry about seeing the future or not. Okay. So finally, to apply the ADMM, we just do the following. Okay, our function f is just going to be kind of a direct sum of these fi's, of xi's. Okay, so we just split this x, this, you know, this variable x is a variable that's defined on this entire grid. And then I just basically take the columns of that grid, apply the cost function, add up all this. It's basically separable function here by scenario. And then this g of z, this function g, is the convex indicator of this and non-anticipativity subspace. Just says 0 if you're on that subspace, plus infinity if off the subspace. And then this m, this linear map from x to z, just drops the individual, just drops the last stage variables from each of these guys. So it drops the last stage variable from x1, from x2, et cetera, all the xm. Okay. And you do this, that stochastic program is just minimize this problem here, okay, is just minimize f of x plus g of mx. Okay. And so if you apply the ADMM and do a little, in particular, consider what this, you know, basically minimizing the augmented Lagrangian when you just have this function to worry about is just basically projecting on this subspace. So you get the following thing. Okay, that you look at all the scenarios individually, you minimize some linear quadratic perturbation of what's going on in that scenario. So you just look at each scenario individually like you could see the future, but now you have this quadratic perturbation here. You minimize all of those, and you get some x's, okay? You drop the last stage variables off those x's, and then you project onto this non-anticipativity subspace, and that gives you this zk plus 1, which is actually an estimate of the solution. And then you update these Lagrange multipliers basically based on how much disagreement there is between the information you had in the individual scenarios and what the average ought to be. Okay. And now, it wasn't obvious to some people, this was kind of not obvious, but you will always have in this case that the Lagrange multipliers are in the orthogonal complement of this non-anticipativity subspace. Okay, and there's several ways of seeing that. One is that, okay, this, if you start there and you have here this, you know, basically when we project mx onto z, when we project onto a subspace, the distance, you know, the vector we move by has to be in the orthogonal subspace. So we always use this, we're just accumulating vectors that are in this subspace. Okay. Another way is, you note in ADMM, it turns out that the multipliers always have to be, you know, the multipliers you get at a particular step are always in the, this might be, yeah, actually, this is correct. So the multipliers you get at a specific step are always, you know, in the subgradient of g applied to this variable z. So this holds always in the ADMM. So and that would basically give you this same result. Okay. And just a little aside, there's an algorithm. This is actually also a special case of an algorithm called Spingar's method of partial inverses, which is basically what's called Douglas-Radford splitting. Any time that one of the operators you have is basically comes from this type of function, where you're just the indicator function of a subspace. Okay. If you write everything out in detail, like in the Rockefeller and Wetz paper, you get this thing. But this is just kind of a long-winded version of what I had on the previous slide. And the condition that you're in the orthogonal subspace, that the multipliers are in the orthogonal subspace, basically means that you take weighted averages of these multipliers over scenarios they have to be 0. Okay. If you don't use that weird inner product I talked about, there is the possibility you can get a different version of this where all that averages you're taking are just simple averages. But then the probabilities appear here in this step here, as opposed to be, so you kind of have a choice. If you use a simple inner product, standard inner product, the probabilities appear here. If you use this weighted inner product Rockefeller and Wetz used, then the probabilities appear in this step instead. So they can either appear here or appear there. You have a choice. Okay, so this is what generically we call a decomposition method. Okay, so and there's many of these in the world, but the general form of decomposition method, you have some perhaps very big problem that you can't solve by a standard method. Uses too much memory or too much computing power or whatever. You say maybe too big for simplex or interior point or something like that. So you break it down, but it's the general form. You break down this thing into sub-problems, break it down to smaller optimization problems that are tractable with standard techniques. Okay. And you solve those. Okay. In this case, there's essentially one for each scenario. Then you have some coordination step that updates some information. Then you solve another bunch of sub-problems, then coordinate, and again. Okay. So in any decomposition method, the sub-problem computations can be operated in parallel. Okay. So in decomposition methods in general, you can do all these at the same time. If you have a parallel computer, same here. But the coordination steps possibly could be a serial bottleneck that you'll never be able to speed up, like no matter how many processors you have. Okay. The nice thing about progressive hedging is the coordination computations are just sums and averages and simple vector operations. Okay. So that's generally, so other decomposition methods like Danzig-Wolf, Benders, et cetera, tend to have some kind of master problem where, do the coordination, you also have to solve another optimization problem. And so this is what you have in progressive hedging is much simpler. So therefore it could be, less of a bottleneck. And furthermore, because it's so simple, it's actually quite easy to do these operations in a parallel way. There are nice kind of distributed algorithms for taking, like an average or a sum of a whole bunch of vectors. Okay. Another great thing about progressive hedging is it handles multi-stage problems very nicely. Okay. So some of these other methods like Benders, it looks nice for a 2-stage problem, but then for a 3-stage problem, you have to use some weird nested version of it, and it's can get ugly pretty quickly. Nice thing about progressive hedging, even if you have a lot of stages, just changes how you compute these averages. It doesn't really change much else. It applies, the theory applies to any convex problem. Some of the others, might be more, only for linear problems. And superficially, you can generalize it to non-convex and integer problems pretty easily. Okay, I mean, the generalization of the algorithm to non-convex case and integer variables is pretty straightforward. Though you may lose, you may have a problem in that you may, you lose the convergence theory and you get more of a heuristic in some cases. So that's progressive hedging. Okay, so that's not really my work, but it's just something historical, maybe presented a little different way. And it didn't have a big success initially. Its convergence speed is not really outstanding. Okay. Sort of on practical problems, it really didn't have outstanding performance, and people kind of said, well, this is a kind of interesting curiosity, but we'd probably not use it. But because of its relative simplicity, it's become more popular again because problem instances are getting really big that some organizations want to solve. And there's increased interest, especially say in power systems on problems that have a lot of stages. And parallel computing is getting more available than it used to be, so there's more interest in algorithms that can more efficiently take advantage of parallel computing. So kind of 20 years after it was invented, it's a sort of somewhat similar story to the ADMM. People start to notice this and say, oh, maybe this is an algorithm you should actually use. And it was incorporated. There's this thing called PySP, which is part of PyMO. So this is one of the first Python-based modeling systems. So, and then built on top of that was a stochastic programming system that uses this algorithm. Okay. And there has been some recent theoretical work about applying it to integer problems a little bit more rigorously. Okay, so now let's see how we're doing. All right, so the issue with the classic progressive hedging algorithm, I mean, one problem with it is it's completely synchronous. Like it says you have to solve every subproblem at every iteration. So I have to recompute every scenario at every iteration, and the coordination step has to wait for the slowest one. So imagine you had a situation where solving these subproblems took some like significantly variable amount of time. I basically solve every subproblem. Some of them get done earlier than others, and you just have all this idle time while you wait. You have to wait for the slowest one in order to coordinate. Okay. Okay. And there are things you could do about this. You could pack the multiple subproblems into processors and try to load balance, but that's not always the easiest thing. You could use, maybe some advanced bundle methods instead. But I'm going to talk about here is using projective splitting instead. Okay. Okay. So projective splitting is an area I've done a little work on some other versions of it with MyCon. But I don't know. I have to give some background because I heard that people here don't necessarily know a lot of convex analysis. But it's basically based on these things called monotone operators. So just like take any Hilbert space and imagine a set valued map T on this Hilbert space. Okay. And so the idea is this set value map is called a monotone operator if I take any two points. So I take 2 points, x and x prime, and then 2 points, a point y that's in the image of x and a point y prime that's in the image of x prime. And then it's saying, okay, I must have this inner product be non-negative. So it's kind of generalized as a function being non-decreasing. And you say a monotone operator is maximal if it's not strictly contained in any other monotone operator. So basically you can't expand the image of any of the points without breaking this property. Okay. So if you have a picture in R1, it kind of one of these things. It looks like this. It looks like the graph of a non-decreasing function, except it can have some vertical places. Okay. And that inner product thing says I take any 2 points on this graph, the line connecting them, this line segment connecting them must be vertical or horizontal or have a positive slope. Okay, so it must have a positive slope, or one of the limiting cases of a positive slope. It cannot have a negative slope. Okay, and the kind of maximal thing says, okay, this is a monotone operator. It's not maximal. Like I can add more points to it without breaking that general property. Okay, but if it's maximal, it can't have any gaps, even at the end going out to infinity at the left top or right bottom. Okay, and there's many examples of this. So basically, the single valued map given by a positive semi-definite matrix is one of these. The normal cone map of a convex set is one of these. Okay, I have to go through this somewhat quickly, I'm afraid. the subgradient map of a convex function is one of these. Okay, so that's saying, okay, all the slopes of all affine I take a point like this point and look at the slope of all affine underestimators of this function at this point. Okay, and those turn out to be one of these monotone operators. Okay, and the canonical problem associated with one of these to find a zero, find some point x that is such that 0 is in the image of x. Okay, so for example, if you had one of the if this T is a normal cone map of some convex set, it's just finding a point in the set. If it's the subgradient of some convex function, these points are minimizers. Okay, and okay. There's this thing called Douglas-Ratchford splitting, which is probably more accurately called Liouville-Mercier splitting, but it's a way of solving. I have this problem here. Minimize 0 is in A of x plus B of x, where this denotes the Minkowski sum. And A and B are maximal monotone operators. So the idea, Douglas-Ratchford splitting is some way of solving this problem by only manipulating individually the operators A or the operator B. Okay, never this sum operator, which might have a much nastier structure. Okay, and so Douglas-Ratchford splitting, okay, so Admm is actually a special case of this Douglas-Ratchford splitting, so that means that progressive hedging is also a special case of this. Okay, so I'm going to discuss now a different form of splitting, which I actually originally developed with Bernard Sveider, who's down in is actually in Brazil in Rio at ISMP, or what is it? IMPA, IMPA, and this is a little different than the one I originally developed with him. I'm going to talk about a version I developed with Patrick Combet. So we consider this problem. We have a bunch of Hilbert spaces. We have n+1 Hilbert spaces. On the last n of them, we have these maximal monotone operators, and I have some bounded linear maps that map from this H0 to these Hi. Okay? And I look at this problem. Okay, so I have some x that's here. I apply the bounded linear map to get into the space for this operator. I apply the operator, then I apply the adjoint of the operator. I'm looking for a solution of this, and it basically generalizes this problem. I have a bunch of functions on different spaces, and some linear maps here, and I'm trying to minimize the sum of all these fi of gi of x. So I map these different linear maps that map these xi's into the domains of these functions, apply the functions, and then add. Okay, so basically, if this looks a little intimidating, it's basically just trying to minimize this sum. Okay, and we have this thing we call the Kuhn-Tucker set for, or primal dual solution set for this, and it's basically set of z's and wi's. Okay, such that wi is in ti of giz, and then this linear equation holds. And it turns out it's not immediate, but it turns out this is a closed convex set. And it's pretty easy to see that if I have a point in this closed convex set, then the vector z, the first element here, must be a solution to our problem, because you basically see that in this problem, if I set x to z, and I would get all these I would have all these w's in the images of these t's, and then I apply the GI adjoints to those, add up, and I get 0. Okay. And so it turns out, okay, so this is a closed convex set, though that might not be immediately obvious. And so it turns out if I have any point xi in the graph of this operator, of these operators ti, any xi, yi's that are in the graph of these ti's, okay, so that's just as yi is in the image of xi under this graph ti, under this set value map ti. then, okay, by the monotonicity, and I have a point here, ZW, that's in this target set, this primal dual solution set S, then just by the monotonicity of the TIs, we have that this inner product is non-negative, okay? So I'm going to just take minus all those and add them up, I get this function here, okay? And it must be, if I stick this function, if I stick in any point that's in S, I must get something non-positive, okay? And so what I'm saying, it's, okay, this actually gives you a hyperplane, that a half space that contains this set, okay? Now you may say, well, how do you know it's a half space? Because it's a quadratic function. There's z's and w, you know, they're cross products, cross terms here between the z's and w's. And that looks like it might be a little annoying, but with a little care, you can make them affine. There are various techniques you can use, but I'm just going to say, just suppose we restrict all our calculations to the following subspace where this set of linear equations is true, okay? If we do that, then we know that all these cross terms in this quadratic looking function, turns out on that subspace, all those cross terms have to be 0. So we actually have an affine function, okay? And once we know it's affine, projecting onto, so it's an affine convex. So it's affine, so it's a half space, it's a convex set, and projecting onto that's easy, okay? So we have a general class of algorithms that looks like this. You have some point in a space. So this is a general class of algorithms for trying to get a point in this, in a set S, which is in some abstract Hilbert space V, okay? So you take some point, you choose some affine function phi k here, such that the set you want's on the non-positive side, and I project onto that half space, okay? So I project. And maybe I can over-relax a little bit, I can go a little further by a factor of up to 2, okay? And then I take another half space that contains this thing, I project onto that, and I just repeat. Okay. Okay. So that algorithm, okay, so in the context I was talking about in this, so in the context of this particular hyperplane and particular affine, you know, context of this particular hyperplane and set I'm talking about, what you can do, you just pick some xik, yik in the graph of each of these TIs and use the above construction, okay? So it turns out this involves, I find some u, which is a projection onto this space w, where those linear equations hold. I project that. I project the x's onto this, and I compute sub v this way. I compute this gamma is like a little scaling factor between the primal and the dual. I don't want to go into it now, but I basically compute this sum. I compute this squared norm here. I basically compute a step size like this, like how much I'm on the wrong side of the hyperplane, if at all, and then I take a step. Okay. So this kind of generic algorithm, which is rather simple, in this more complicated context, it looks like this. Okay. So let's see. I don't have a ton of time left, but so anyway, it turns out there's a way. So the question is, okay, that's fine, but how do you pick these xi's, yi's? If you don't pick them well, you'll just kind of orbit and you'll never converge to the set you want to converge to. It turns out that you can use this, what's called a prox operation, okay, which is basically this weird looking quantity in here, basically means I just minimize a quadratic perturbation of the function and then do some simple calculation. And that, if you choose the xi, yi's in that way, then it turns out you get a convergent algorithm from this approach. Okay. Now, what I showed with Patrick Combet is some interesting things, like you don't actually have to pick up every function, every operator every time. Okay. You can just do a subset, like, an iteration, k, I do some subset ik. And so long as they have this property that there's some integer m, such that if I take the union of these subsets over any m consecutive iterations, I've actually looked at everybody. Okay, so I can be unfair, but I can't. There's sort of I have to look at everybody at least once every m iterations, and there's some boundedness about how unfair I could be between these different operators. Okay, so what we can do is, for the things we want to look at this iteration, we do this like prox operation, and for the others, we just use the old one. Okay, and it turns out this still works. And then you can even have lags. Okay, so you can even you can use old data for the ones that you do work on, even though just has to be some bound on how old it is. Okay, and that means that you can actually now operate in an asynchronous way. So with those two things, you can kind of imagine the following process, where I suppose that for each I do one of these, like the Z, and just think of the Z and the W. So this is like a primal solution kind of implicitly as a function of time, Wi, dual solution implicitly a function of time. For each I, at least every T1 time units, I do one of these calculations, and it's based on something that's at most T2 time units old. Okay. And then there's some other time span during which I do one of these projections every T3 time units based on data from here that's at most T4 time units old, and then I still get convergence. But the idea is kind of here, like I drew a picture of my kind of 6 scenarios here, 6 subsystems. I can kind of work on each one in a sporadic way, and then I can do these projection steps based on data that cuts across these these different systems in a kind of uneven way, so long as it's not too distorted. Okay, and so it turns out now you can apply this. That's all right, kind of jammed a lot of stuff into not much time there, but you can solve stochastic programming this way. Okay, we set our master subspace to be this non-anticipativity subspace I talked about. Set the individual HI to be the Z, which the decision variables for scenario I, okay, not including the last stage, and the inner prog multiplied by pi. The GI is a linear map that just selects the scenario I variables out of this subspace. And then you define Fi here for each the individual n functions. Each of them is just, you take all the variables except for the last stage, and then you just optimize over the last stage, and you multiply by pi. And then the stochastic program with this setup just becomes this problem, and we apply that method I was talking about. And you get so here's some technicalities about which I think I'll skip. But you get the following thing. So you have subproblems that look almost exactly like progressive hedging. Okay, you accept that you can actually pick the penalty parameter. It does in progressive hedging, it has to be the same for all time and the same for all subproblems. Here it can vary with time and it can vary with subproblem. But I just pick some penalty parameter. I solve a quadratic perturbation of my problem for the individual scenario. I update some Lagrange multipliers, and I hand that, and the Lagrange multipliers basically go into this Y, and I hand them back to the sort of master problem. Okay, and this is rather long and complicated, but essentially you get, so basically the Z is the solution, this Z is the primal solution, W is the dual solution. But if you apply this projective splitting method, you get the following thing where you basically, the coordination process looks at all the recent, gets some data from recent values of the data from all the subproblems. It basically projects the x's onto the orthogonal complement of the non-anticipativity space. It projects the y's onto the non-anticipativity space, computes a step size here, takes a step. Okay, but this stuff, it looks a little complicated, but it's just doing that projection in a particular high dimensional space. And this thing, it looks sort of, it's just simple vectors and averaging operations. It doesn't actually have to be centralized. It can actually also be decentralized over a parallel computer. And you get the same type of asynchrony. Okay, so you get this algorithm that looks a lot like progressive hedging, has essentially the same subproblems, the same operations in its coordination process, except a little bit more complicated, but basically qualitatively the same. So the control process is similar, but a little more complicated, but it can be still the same general types of operations, and it can be implemented in a distributed way, but now it's asynchronous. Okay, so the full synchronization has been replaced by kind of loose timing bounds. The subproblem coordination process can run at different speeds. You're kind of no longer locked in to having one coordination step for every n subproblem solves. You could coordinate more frequently, for example. So here I just have a few more minutes, but this is the kind of computational work we're doing at the moment. So we're looking at a kind of classic problem among stochastic programmers, which is a telecommunication design problem from Suvrajit Sen. It, has, in theory, it's finite, but it has like 10 to the 70 scenarios. And we solved this on a big computer at Lawrence Livermore Labs in the US, using this software that's under development, this NPI SPPY. So it's this Python-based stochastic programming platform that was developed originally at Sandia. So these kind of systems, they're big beasts of a system. They're getting kind of common though, at least in some countries. So you have so each node of this, okay, usually consists of 2 CPU chips, each of which has a bunch of CPU cores and a bunch of RAM, and these all share memory, and then there's some interconnect between them. Okay, so this is the system that they actually have there. So it has 32 cores per node. Okay, so I think it has like 2 16-core chips per node, 128 gig of RAM per node, about 3,000 nodes, and this omnipath interconnect. So it's a very fast network in between them. Actually, this is wrong. We actually went up to 500. So we actually went up to 16,000 cores and 500 nodes recently. So anyway, so the software, it's a little complicated to explain. But it's built on this PyMO modeling system, which is built on Python. It's coded in Python, but generally most of the CPU time is spent in Gurobi and in linear algebra kernels, like BLAST kernels. And they use the MPI, just refers to a standard way of communicating between parallel processes over a network. And it has what they call a hub and spoke architecture. I guess I'll skip the lower bound stuff because I think we're short on time. But basically, one issue with both progressive hedging and our alternative is, while you get like theoretical convergence to a solution, you don't necessarily get lower bounds on the solution like you would in Lagrangian method or augmented Lagrangian method. So they kind of tend to run a parallel process to generate lower bounds. And you also don't sort of get a feasible solution till the end. So they also have a parallel process to kind of feed off the main computation and try to heuristically generate feasible solutions and therefore upper bounds. So they kind of use the following organization where you have a bunch of processors in the middle. Those are called hubs. That does the progressive hedging or asynchronous progressive. It does the basic convergent algorithm, and then you may have other groups that they call spokes. We have other groups of multiple processors which are, say, trying to find lower bounds or trying to find upper bounds. Okay? And a rank is a single shared memory space, typically 4 CPU cores. We actually went up to 8 in the runs I'm going to show you. Basically, you want to, whatever you're using to solve those quadratic programs like Garobi, you want to be a number of processors it can use efficiently. You pack multiple ranks onto nodes of the supercomputer, and then you organize into these kind of cylinders and strata. So cylinders are sort of basic. This is the basic convergent algorithm. This is the heuristic for, this is finding lower bounds. This is heuristic for finding upper bounds. You can have multiple ones of each of these. And then each rank here is worrying about a specific scenario, okay? And you basically only communicate laterally between ranks that are worrying about the same scenarios. Okay. Basically, I may kind of skip this as well, but this is kind of the overall organization that you have. Now, for big problems, we do something called bundling. So instead of having individual scenarios, we kind of bundle like groups of, like, say, maybe quite a large number, maybe even 1,000 scenarios together. And those become, so the scenarios of the scenarios in progressive hedging or asynchronous progressive hedging are actually groups of scenarios from the original problem, but they still have to be related to each other in exactly the same way. So this example with 20,000 scenarios, and this is like the relative gap between the upper bound we've generated and the known optimum. This problem is huge, but within the grasp of solving, say, with Garobi, if you have a huge amount of memory. Okay, and you see, well, the asynchronous. So here we're just running so far the asynchronous progressive hedging in its synchronous mode. So it's actually doing exactly the same subproblem calculations, really, as progressive hedging at each step, just does a different coordination, and it does a little bit better, but it's not like a big deal. Okay, and this is with 1,000 scenarios per bundle. There's always one bundle per rank, 8 cores per rank, which is Garobi can use those efficiently, 8 cores for these problems, solving QPs, 2 cylinders of 20. So we're using 320 cores total on 10 nodes of this supercomputer. Okay. This is a problem with 1 million scenarios, so we don't actually know the optimal solution, but so I'm just printing the objective value here. But this is 1,000 scenarios per bundle, 8 cores, same thing. But now we have 2 cylinders of 1,000 ranks, so we're actually using 16,000 cores or 500 nodes to solve this. I think the actual solution is between 10.2 and 10.15, but you can see, anyway, we're doing a little better here with our new algorithm, but it's not much. Okay, but that problem has 795 million variables, 265 million constraints, like 2 to 3 billion non-zero coordinate matrix entries. So the synchronous mode performance of our new algorithm it's marginally better than the old one, but it's not a big deal. But based on some stuff I've done on other problem casts, I expect this to improve a lot if we can do things like not having to solve every subproblem, every iteration, overlap communication, and computing, all things that the new algorithm allows you to do and progressive hedging doesn't. Unfortunately, the software is not functioning yet. I'm kind of depending on Dave and JP for that, but we're making progress towards it. And this is some stuff we can do in the future, but I think I probably shouldn't talk about that either. So, okay, I think I'm going to leave it there.
Okay.
Oh, That's cool. I
Okay,
have
we're back.
I have like a recursion here.
Okay.
I can remove that for a while.
Yeah, whatever.
Okay.
Okay.
This is it.
So do you have? Thank you very much for.
Yeah.
Your
I know that's a lot of stuff to pack into an hour. So I expect people to be confused.
So people can learn. Now people know what they have to learn. So that's good. And thank you very much. Very impressive results.
So Maikan, did I show you this before? Did I show you this application before? Yeah.
No.
Yeah.
No.
I mean,
really...
I mean, you don't use the forward steps. Okay.
Okay.
Because the forward steps are hopeless on these, these non-smooth subsystems, right?
Okay.
But it's the same basic idea. Yeah.
Yeah, nice. But we have time for questions, so Antonio can help me to manage to display possible questions from the audience.
I've been monitoring the chat here, and so far there are no questions.
Yeah.
But we have also to count with a small delay between the transmission and the YouTube.
Yeah.
And so let me start. You mentioned the non-convex case.
Right.
And you also mentioned that there is little theory to support convergence analysis or something like that. But as you observed, I mean, for instance, in terms of progressive hedging, can be seen as a special case of the Admm and so on, and you observe that all of this is proximal point. But we know some proximal point versions for non-convex problems like N and N and some variants.
So this could be interesting to look at.
Okay.
Yeah. I think that would be interesting. I mean, the question, I mean, it kind of gets filtered through, you're doing when you're doing Decomposition Method, you're doing proximal point on this like weird skew operator, and who knows like what you'd be able to do with that, right? I mean, the theory that's been developed so far, so like Dave and JP just tried it, and they did they just said, okay, we have these big power systems, we want to plan, we don't care if it's heuristic, but we want to try to get some kind of decent plan, right? And so they tried it, and what they find is, they'll get solutions, but the binary variables will tend to cycle. They'll tend to bounce back and forth. I mean, you can take a smooth relaxation, solve that with this decomposition, and then try to do branch and bound or something. But so far, no one's ever gotten that to ever had enough computing power to get that to work. The interesting results that have come out are like, it's been shown that if you do a small modification of the algorithm, you are at least computing the Lagrangian bound of the integer problem, which is stronger than the LP relaxation bound, because you still have integer in the subproblems. And you basically, you have to make a little, you solve the subproblem. I mean, this is for progressive hedging. You solve the subproblem, and then you just project onto the convex hull of all the solutions, integer solutions you've seen so far. So you solve the integer subproblem, you take the and then you project, you take the actual solution, you return to them is, you return to the master is formed by projecting onto the convex hull of all those solutions. And I think that would work. I think that same trick that they use to show that works would also work with a projective splitting as well. But we haven't actually done the theory, but I think that would also work there.
Okay, very nice. Very nice. Good ideas.
Yeah, but I'm not. So what did Pananen do for non-convex proximal?
Yes, I think he did.
Was it like a hypoconvex?
Yeah, I think so.
Yeah, I think the issue is for any realistic problem that people care about, ever computing this, constant of hypoconvexity.
Okay.
that
I
could be
see. I
written
see
down.
people working with the weakly convex functions. I mean.
Yeah, that's I call them hypoconvex. I don't like weakly convex.
Okay, this is an operator version of these. I mean.
Yeah, but no. I mean, I don't like the term weakly convex because to me it just means it should mean like convex but not strongly convex.
Okay.
It shouldn't mean non-convex. I call those hypoconvex, but yeah, the issue is that okay, there's some quadratic perturbation you add to the function that makes it convex, but I think for these realistic, for the real problems, integer problems people want to solve, like power system planning and so forth, getting a handle on this constant is really challenging. Right?
Okay. So, Antonio, do you have?
Yeah, by the way, I do have a question. You mentioned parallel computing, so
Yeah.
I'm actually involved in these last weeks with parallel computing and parallelizing iterative algorithms. So, just a question: how better does the algorithms become when you do use this procedure that you are describing with so many nodes and so many processors in order to accelerate the execution of your code?
Well, yeah, the nice thing about, progressive hedging, the speed up's almost linear.
Oh, I see. That's nice.
Yeah, because, I mean, the issue is, because, you just have to take some global sums, basically, and they're very efficient algorithms for that. That are just, the time is proportional to the log of the number of processors. Okay. The issue is what you're speeding, progressive hedging is not necessarily the best serial algorithm. So, it's always this game of like, okay, I take an algorithm that's, not the best one in serial. I speed that up a lot. How much am I winning really?
I see.
Yeah. The problem is for like the classical, so generally speaking, the best algorithms for, large, for big, nasty, say, quadratic programs, even convex, is barrier. Okay, it's Newton barrier method, right? But the problem with that is that they kind of have this n cubed amount of storage that they need. So when you scale to really large problems, you generally just hit a wall. So that's why people would try to turn to a decomposition algorithm like this. And the decomposition algorithm has excellent speed up properties within itself. Okay. But yeah, I mean, there's certain algorithms. So like I've also worked, this totally different, but I've worked on branch and bound, and within certain ranges, you can get I mean, linear speed up in branch and bound is not hard to get either. It's harder to get, but it can be done. But yeah, there's certain, the efficiency of these things relative to their serial versions, these type of algorithms, is very high. The question is the serial algorithm may not be the most competitive one for smaller problems. Yeah.
Interesting. Okay, thank you. Thank you very much.
Yeah. So what's your background, Antonio?
Michael, there are some new questions. Sorry,
okay,
Jonathan.
Good. Yeah, okay. Where are they?
There are some questions here I can put them on the screen.
Oh, Wellington. Okay. There we are.
But there is this first one here, in order of appearance.
Yes, is the answer. And actually, Maikan has already worked on this. Actually, yeah. Yes. This can be done. Yeah.
Yes, we are working on it. I can send this material that actually available on the archive. I can send it to Paulo.
Okay.
A question from
Wellington. Wellington, yeah. So, I think the main issue is yes, it can handle risk averse is the short answer. Okay. The longer answer is when you have a lot of stages, risk averse becomes really weird. You know, that you need these, like, you lose time consistency unless you do, unless you do like a nested version of these. Are you talking about like coherent risk measures and things like that, right? Yeah, I don't know if Wellington can answer, but yeah.
Yes.
Yeah, so suppose you do something like conditional value at risk, or mean semi, all these things. Yeah, I mean, for 2 stages, absolutely. Okay. And if we use this kind of nesting of list measures, I don't see any reason why we couldn't adapt these methods. The issue comes in that you can have really weird stuff happen when these risk measures that allow you to be time consistent are not, they can be not law invariant, so you can get like two solutions that have actually the same exact distribution of returns, and one is rated riskier than the other. So you can get bizarre things going on there. But fundamentally, I don't see as long as you're working within things that can be modeled with convex programming, I don't see an issue. I think it can be done.
So this was the last question so far. Yeah. Please, Michael, proceed.
Yeah. No, I'm okay. I have no more questions. Yeah. Just to thank you very much for taking some part of your time to talk to us.
Sure. Yeah. So Wellington is in France, though, right?
I don't know. I think so.
Yeah.
Okay, guys.
Okay. So I didn't expect too many questions on students because that thing was really pretty dense. But I'm glad I got some questions from professors anyway.
Okay.
Yeah. Okay. Good. So anyway, hopefully we see each other someday, right?
Yes. Let's wait for the best.
So thank you, guys. Thank you both very much for participating in this conference today. So,
okay, thank you. Okay,
bye. Bye-bye. Thank you.
Bye-bye. Muito obrigado a todos. Assim terminamos o colóquio dessa sexta-feira. Muito obrigado, Michael, por ter indicado o professor Jonathan para palestrar aqui hoje para a gente. Então, terminamos assim a nossa transmissão de hoje. Isso parece o rádio, né? De antigamente. Até a próxima sexta-feira.
Leva jeito, Antônio. Pode tentar uma nova carreira.
Pois então, tem que treinar mais a voz, né? Ficar mais impostado, enfim. Se cuidem, que a pandemia está pior do que nunca, enfim. Um grande abraço a todos, até a próxima sexta-feira. Muito obrigado. Um abraço.
Tchau, tchau.